good morning, good night, good afternoon to everybody. I think maybe it's afternoon in Australia and New Zealand. I think it's definitely the morning time in Asia. Good morning. It's definitely very early morning in Europe. Very good morning. And good evening, Americas. Hello. Hola. Hello, 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 hello. Ooh, here's a song for you. Good morning, pineapple. Looking very good, very nice. Good morning, pineapple. So while we wait for everybody to join, I'm going to share the live right now because usually I forget for many, many minutes and people are generally not always getting the notifications pushed out. So I'm going to share the live. Thank you for being here. Look at my lamp. So I've pointed the lamp that way. I have this table lamp because I don't have a ring light, and I'm using the diffuse lighting of this room to sort of make do for the moment. I think diffuse lighting is better than a light on my face. So that's how things be at the moment. Thank you for your patience with my setup here as the channel continues to grow. And thank you very much indeed for being here. Ooh, I forgot to say what we're going to be talking about today. I'll say that right here, right now, real quick. And usually when people join, so if you're seeing this as a video upload later on, you'll see how it kind of rolls. Usually when people join, I will sort of try to read all their messages and give a shout out to the people who are kindly leaving a comment, especially if it's a good one, especially if it is, speakable, or if it is, not despicable. Then I try to read it out and I try to give everybody the acknowledgement and appreciation and of course the thanks for being here. Welcome, welcome. Thank you so much for joining the live and all that. And I usually will catch up with everybody. We show the kitty cats too. See, they're over there, and there is usually a nightly Zoomy time that they have. And then we get into more of the material and the topics, and we have been discussing cosmology. So yesterday I talked about cosmology and we left off where we were going to start talking about Big Bang nucleosynthesis. We might be catching up there, starting exactly there, and then we might even have time for the moons of Jupiter and Saturn. Hello. Hi, Neeraj. Hello, namaste. How are you? Wishing you a fabulous morning, says Neeraj. Hi. Thank you for being here. Neeraj, can you do something where you share the live with some friends or something? I would like to have more people joining today if possible. So any help at all to spread the word on this live would be amazing. Amazing. Hello, hello, hello. Welcome, welcome, welcome. Come on in, come on in. Come on in and get yourself comfortable. Get some popcorn, get some hot chocolate, get some tea, get some water. We are live. Welcome. Hello. If you say something in the chat, I will give you a oh, here's my voice over here. I'm trying to share the live. If you say something in the chat, I'll give you a shout out. Oh yes, please do like the live. Thank you. Thank you for liking the live. Thank you so much for being here. Welcome. Welcome, welcome, welcome. Welcome, Neeraj. Welcome, hi, says hi. Welcome, Bucky, says Indian descent. Descent. D-E-S-C-E-N-T, I believe is the word. And we will leave that as a mystery. Let other people join, and some of them might give it away for you. So I'm waiting for the mods to be here. They have interesting things to say about my origins. So let's keep on going. What are some more guesses? What are some more guesses? Mexican. Ooh, hello. Hello, hi. Hello, Bucky. Hello, Whittlin. Hello. Hi, Kevin. Spence. Colombian. Oh, wow. Kevin is guessing. Got it. Colombia. Colombia. Well, thank you everybody for being here. We are live. We are live. I just shared the live, so I'm hoping that a few more people will be joining very soon here. Hello, welcome. Welcome, welcome, welcome. So I might just get started actually without further ado, because if people join and start to message and send comments, Jakarta, I love it. I can always stop in between and read these comments. Where are my moderators? Where are you? Reese and Doro. Actually, Doro is traveling, so maybe they can't. It's entirely possible that some people cannot join today. Hi, Venkata. Hola. Oh, that's right. I think Venkata was here a couple nights ago. Venkata, were you the one who was at my Planets Live, or was it about, or were you here for the Cosmology Live? This channel is all about kitty cats and physics. So basically, this is a booktubing, book club vibe kitty cat channel where we show the kitty cats or we show me, and either it's kitty cats and my voiceover talking about various books generally in the topic of physics, astronomy, astrophysics, and cosmology, or it is my face talking like this to you guys along with the kitty cats in the background talking about the same topics. So that's what we're doing, okay? Witolin and Kevin Spence brains. Is this about Vedic astrology? Indeed, it is not. KC 154. Hello, Kevin. Hello, Venkata. Hello, Witolin. Hello, KC 154. Hello, Bucky Barnes. Hello, hi. Hello, Neeraj. It is indeed not about Vedic astrology. I don't think I know a lot about that topic at all. So it's not about that. We're going to be talking about physics, cosmology, astronomy, astrophysics. More like. So, Iran, Persian. Mustafa says, I am Iranian. Physics 101. It's not going to be Physics 101. So, let's see. Let me get started and perhaps you can get a better feel for what we're talking about. So, yesterday, basically, for a few lives, let me give you a little bit of background. Basically, in the month of November, we covered in some detail 20th century physics, or what we consider modern physics. So when we say modern physics, it doesn't have to be the most modern, most current type of work, but more like what happened in the 1900s. And even then, I mean really in the first half of the 1900s. So things like relativity, special theory of relativity, general theory of relativity, photoelectric effect. So the old quantum physics where we found that light has a quantum nature, a particle nature, is considered the old quantum physics, right? So we actually covered in some depth the work of Einstein from those years in the early 1900s. So in the literally the 19 somethings, the 1920s and such. So we covered a lot of that. So if you're interested in those types of physics topics, a lot of that is in the live streams that we have done in the month of, I believe, like October, November-ish. Then we started talking about a bit more current stuff. So of course we covered how quantum mechanics has succeeded a lot. And even though it was considered sort of a bizarre science, all the physics of the very small, it's not really classical. It has this uncertainty nature, right? The fact that your answer in quantum mechanics is not deterministic, but it is probabilistic, was very new to people. Even some of the sort of inventors or the heavy contributors of quantum mechanics were not good with that. They were not comfortable with quantum mechanics, of course, being probabilistic versus what they're used to so far, such as in classical physics, which is to be deterministic, where if I told you the position of the moon as a function of time today, you could probably predict it for me 1,000 years later. So that is how deterministic classical mechanics is. But quantum mechanics, if you write down the position of something as a function of time for a little particle like the electron of the hydrogen atom, it's actually the probability of finding that electron that we get, not the deterministically exactly where it will be. So that was that was very uncomfortable for a lot of physicists, a lot of the classical physicists, and even some of the quantum physicists. So we covered this type of very fun topics at a lot of depth, and we had a lot of fun with it in the months, in those types of months, like October, November. Then we moved on to slightly more recent topics like particle physics, particle astrophysics, which is my background. And also, we started to think about the universe because on this channel and pretty much in general too, pretty much the biggest questions of the universe today are, of course, what is dark energy, what is dark matter, and the origin of elements. And I mean the elements that we don't quite know exactly how they're made, in what exact process in the stars. We know that every element above helium is made in stars, we know that, but there are certain more details, like the processes in which elements are made. Some of the elements are very well understood, and there are still some that are not as understood. So in short, those are the three questions that we talk about here on the channel quite a bit: dark energy, dark matter, and origin of elements. But also, I mentioned them as the motivation for pretty much all of the more current research. It's not that we're always talking about exactly those topics, but just to give you context on the more recent work, where it's at in the world of physics. So basically, more recently, in the month of December, we started to talk and cover a lot more about cosmology, which is the study of the universe. We also talked about how astronomy, astrophysics, and cosmology are all kind of different from each other. They all have overlapping parts, but the universe and studying it, everything from the Big Bang, which is the topic today partly, as well as the early universe, as well as its evolution, as well as the fact that it's expanding, as well as the fact that we don't quite understand what dark energy is, which is, of course, responsible for the expansion. Those are the things we have been talking about in the month of December. What is this month now? January. So in January, we started to also cover a ton of particle astrophysics. So this is still answering the question about what this channel is about. So we talked a bunch about particle astrophysics. That kind of motivated me to talk about gamma ray bursts, which is, of course, a very interesting astrophysical source for me, for potentially something like neutrinos and other extragalactic accelerated high energy particles. So that is how I also ended up covering supernova and stars dying and stellar remnants, what stars end up as. So more of an astronomy, astrophysics type of topic. I will drink some water. But then we started to talk. I realized that we did not talk too much about our own home solar system, which is the sun, planets, us, the terrestrial planets, the rocky metallic planets, Earth, Mars, Venus, Mercury, as well as what we call the Jovian planets, which is Jupiter-like planets, which is Jupiter, Saturn, Uranus, and Neptune. So we started to talk about that as well. For a few lives now, we were talking about the planets. Today, if we have time, we might talk about the moons of Jupiter and Saturn. I have been covering astrophysics from this textbook called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. And also, I have a book for cosmology, which is called Modern Cosmology by Scott Dodelson. So these are some of the books that I use. I have other books too, though. So that is kind of what you might expect here. Let me read some of these comments. Do you know where Iran is? Indeed, I do. Thank you for the interesting shapes, focus star, wand, fortnight. E equals mc squared. Yes, indeed. So yes, we covered things like that in the sort of the modern physics category of things that I was mentioning. So, everybody, are you ready for some cosmology? Because that's what we'll cover today. So, let me recap a little bit what we talked about yesterday. So, I realized that when we talked about the planets, right? So, the planets are very specific. So, by the way, when you study something like the planets in our solar system, like the Earth, Mars, Venus, Mercury, Jupiter, Saturn, all those types of objects, which are pretty specific, are more of an astronomy topic, right? Something like learning even about other sources in our own galaxy, that's more of an astronomy topic. If we wanted to understand the processes happening within a specific event, such as, say, a supernova, that would be more of an astrophysics topic. So those are the astronomy, astrophysics type of definitions or examples that I wanted to give you as to what I mean by them, right? But what came up when we were specifically talking about, I think, Jupiter was, well, Jupiter, it has a tremendous amount of pressure in its center. So much so that there is a certain layer in Jupiter which is metallic hydrogen. So Jupiter is very, very different than Earth. It's much, much bigger, 318 times bigger in mass than the Earth, for example. And the environment is very different. So that kind of motivated us to talk about just in general how different the universe is too, because the fact that hydrogen is important on this planet like Jupiter kind of reminded me, well, maybe I should talk about the universe as a whole once in a while. I have talked about the universe in my more cosmology lives here and there, but sometimes I think it's worth kind of pausing everything and talking about the universe again, because when you really zoom out and don't consider specific objects and specific events like stars and planets and supernova and how stars die, those are specific objects and specific events, more of an astronomy, astrophysics type of thing. Then you really consider the entire universe, right? The universe. Say if that is our zoomed out, more broader topic, then I also asked this quiz question: what is the most abundant element in the universe? And I think most of my audience members at this point know what that is, but I'll let some of you take a guess if you'd like. But basically, that's sort of more the focus when we talk about the entire universe. And we talked about how the universe, after it got started with the Big Bang, of course, it was very radiation dominated. So photons were what I call the king of the jungle back then. And it was a very different type of universe than what we know now. And later on, it became a more matter dominated universe. And we thought maybe non-relativistic matter is what is governing the universe at this time. But we saw actually that the universe more recently has taken another turn and evolved towards being dark energy dominated. So we covered this in more detail just last night, but basically we talked about the cosmic inventory. So broadly speaking, what are the ingredients of the universe, as though we're trying to bake a cake? And we do know the ingredients of the universe, but I'm not sure that we still understand exactly what everything means. I know that we don't, right? So really fast, the 5 ingredients are photons, baryons, dark matter, dark energy, and neutrinos. Out of these 5 things, we understand photons, baryons, and neutrinos. We don't understand dark matter and dark energy, as in what these things are. So we talked about the sort of evidences from a cosmology point of view, from a cosmology standpoint, for needing dark matter. The fact that there is dark matter, there is this invisible matter. We don't know what it is exactly. It doesn't interact with light. It doesn't interact with electromagnetism, but it does interact with gravitation. And we know that there is this extra stuff that we have to still kind of explain. So all of the different types of observations and evidences that give us this is something we talked about yesterday in the, I believe I called it, whatever it is in my live tab. I think I called it universe, cosmology, something. And so, hi says something. And so we talked about that. Dark energy was another thing. We looked at some very interesting observational data in the form of supernova data, actually, that gave us basically the supernova at a lower redshift compared to a supernova at a higher redshift with the same absolute magnitudes, but having different apparent magnitudes of their luminosity gave us an evidence for dark energy. So we talked about basically when you think about the universe's expansion, pretty much that is definitely a cosmology topic. The answer lies within how we approach this in cosmology as dark energy. So turns out nowadays in our current universe, dark energy is the dominant. It's the 70% of the critical density of the universe. So we found that baryonic matter, which is ordinary matter made up of neutrons and protons, is, thank you, is 5% at most of the critical density of the universe. Dark matter is 25%, and dark energy is 70%. So, that's the sort of cosmic inventory that we went through last night. Photons, baryons, dark matter, dark energy, neutrinos. So if you're interested in things like that, we covered that last night. We did not cover Big Bang nucleosynthesis. So basically, the universe is expanding, and then there's also other data to support that there was a Big Bang, as in it wasn't very big and there wasn't really a bang, but we just call it the Big Bang, where basically the universe has been expanding ever since. And certain things were made in the Big Bang / shortly after the Big Bang. So this topic is called Big Bang nucleosynthesis, because you might wonder, well, if you said most of the elements come from stars, most of the elements, if they come from stars, then what about hydrogen and helium? So Big Bang nucleosynthesis is important, especially for this. So pretty much, it's kind of simple. So Whittlin says that it's beyond your comprehension, but you might be surprised by what you learn in this live. But thank you all the same. Thank you nonetheless for being here. Thank you and welcome. Basically, the Big Bang is what gave us hydrogen mainly, and a little bit of helium and trace amounts of lithium. After that, pretty much all the heavier elements and even helium is made in the stars. So Big Bang mainly gave us just hydrogen and then a little bit of helium. If we had more helium back in that time, then we might have even made something like carbon. You'll see how. We will talk about a little bit of nuclear physics in just a little bit here, but we didn't. It was not the most abundant thing to have a ton of helium and have the ability to combine and make carbon. So even for something like carbon, which, as you know, is of course important for our for life, even for something like carbon, you really do need stars to do that. And so even before there were any stars, even the first generation of stars were not there, nothing was there. We're talking really about that particular time, at this time. So Big Bang nucleosynthesis is really before all of that. So as you can see, of course, we have the stars to thank for as far as us being here and all of that, because we come much later, the stars come much later even. And it's when those stars that make the heavier elements die and spew all their stuff everywhere, that is related to where we come in. But now let's transport our imagination back to even before there were planets, and even before there was the sun, and even before there were the stars, and even before there were the very first stars. Okay, and that is where Big Bang nucleosynthesis is coming in. So that's what we'll cover in just a minute. Please do like the live and leave any comments in the chat. Thank you so much. And yes, you don't have to be well versed in the matter in order to get some value out of the lecture, I think. Thank you, though. Ben, are you here? Okay, so long ago, when the universe was getting started, as I was mentioning, it's really the photons were very important. It was a very hot, dense, energetic universe. Photons were hitting everything and making them very excitable, and not letting anyone calm down was basically what things were back then. We call this the radiation dominated universe. And we mentioned also yesterday how the scale factor, which is given by small a, is something that we define out even when our live stream is not very mathy. We still mention the scale factor enough where then I want to kind of define it out again. But basically, scale factor helps us with capturing the expansion of the universe. And we noted that at early times, the scale factor was proportional to t to the 1/2, where t is cosmic time. So even the scale factor's sort of dependence on cosmic time has evolved. As the universe has evolved, so has the scale factor's dependence. So it used to go as t to the 1/2. Later on, in the matter-dominated universe, it goes as t to the 2/3. And then it changed again, and that's where we talked about dark energy yesterday. So I'll just mention that real quick, but basically, there were some relativistic particles in equilibrium in this hot, dense, beginning universe. And what is in this mess of an equilibrium? Mainly, this was just, hello. Mainly, what we had were photons, electrons, and positrons. Batman says I'm back. Good. So basically, at first it was really, really hot. When there was enough of a cooling, and I'm saying this because it's still kind of hot, but there is some cooling relative to the very beginning of the universe. So around when the temperature of the universe cools to 1 MeV, the cosmic plasma consists of the following. So first is relativistic particles in equilibrium, photons, electrons, and positrons, like I was saying. Electrons and positrons are the anti-particle of each other. Photons are, of course, light particles, as you know. These are kept in close contact with each other by electromagnetic interaction. So, of course, you also know that photons, electrons, and positrons all interact electromagnetically. These are all particles that interact through electromagnetism, which is one of the basic fundamental types of forces. And basically, this E plus, E minus going to photons, or the photons going back to E plus, E minus, this type of interaction was happening constantly. So photons hitting things, putting out E plus, E minus, combining to make photons. This was happening constantly in sort of a relativistic soup equilibrium containing electrons, positrons, and photons. Besides a small difference due to fermion boson statistics, these all have the same abundances. So basically, this is saying that soon after the Big Bang, photons and positrons and electrons are at an equilibrium. And even though electrons and positrons are fermions, they're fundamentally different particles than photons. Photons are bosons. So the statistics, this is mainly going to affect their statistics. Fermion statistics is different than boson statistics. But back then, in that hot mess of an environment, we don't care so much about these specifics and these more statistical distributions. We just know that this was just constantly happening. Photons, electrons, and positrons were constantly interacting and in an equilibrium. So that was one thing. Then we have decoupled. Okay. Then we have decoupled relativistic particles or neutrinos. So at a temperature a little above 1 MeV, the rate for processes such as new electron going to new electron, which keep neutrinos coupled to the rest of the plasma, drops beneath the expansion rate. So this is very interesting. Basically, the universe is already expanding, and if your neutrinos that are coupled to the rest of the plasma, if the interactions between those neutrinos and the rest of the plasma is less or is happening less than the expansion rate, you will have a decoupling of those. Where is my moderator? You will have a decoupling of the relativistic particles with the hot soup. I will get rid of you myself. Okay, goodbye. Oh, and you too. 30 minutes for you, Moon. Yay, we can go back. So this is what I call the neutrino breakup with the, oh, there's Baji, by the way. This is what I call the neutrino breakup with the cosmic soup or the cosmic hot soup. So this cosmic plasma, including photons, electrons, and positrons, which I just mentioned above, was in this hot mess kind of constant interaction with each other, equilibrium. Well, neutrinos are part of that, right? So why is it that the neutrinos kind of had a breakup with these cosmic plasma, with this cosmic plasma, which includes the photons, electrons, and positrons? This is because the rate of interaction, so neutrinos are weakly interacting. So neutrinos interact with the rest of the things through the weak force. So neutrinos do not also interact through the electromagnetism force. So this weak force interaction and the processes which let neutrinos interact with the plasma basically drops below the expansion rate, and there is this decoupling of the neutrinos with that plasma. So it's so interesting, but we do have a cosmic breakup of the neutrinos with the plasma. So I'll read this from here. At temperatures a little above 1 MeV, the rate for processes such as nu E, which keep neutrinos coupled to the rest of the plasma, drops beneath the expansion rate. Neutrinos therefore share the same temperature as the other relativistic particles and hence are roughly as abundant, but they do not couple to them. So all that stuff from the initial hot plasma type of environment, we know that pretty much they're going to be roughly as abundant. The neutrinos will be roughly as abundant because those same interactions made the neutrinos as well, but they are not coupled anymore. This will kind of affect the temperature and energy associated with these things, which we will look at separately. But that's the story there with the Big Bang nucleosynthesis neutrino breakup. Dora says, good evening, just gonna be chilling, listening, and learning while I work. Hope you and the chat is all well. Thank you. Well, there was some trouble, but I took care of it myself. So no worries, yeah, you can chill and listen, and that sounds good. So we've talked about relativistic particles in equilibrium, which is the photons, electrons, and positrons. We talked about decoupled neutrinos in the Big Bang nucleosynthesis. Next, we will talk about non-relativistic particles or baryons, which is basically protons and neutrons, and at that point they were non-relativistic already. So if there had been no asymmetry in the initial number of baryons and antibaryons, they both would be completely depleted by 1 MeV. However, such an asymmetry did exist. And so there is a ratio of N baryon minus N baryon anti, basically, over S, which is 10 to the negative 10 initially. And this ratio remains constant throughout the expansion. So it's not like there is the same amount of baryons and antibaryons, which is nice. By the time the temperature is of order 1 MeV, all antibaryons have annihilated away. So pretty much we kind of got rid of the antibaryons, and we get eta baryon, the ratio of N baryon over N gamma to be 5.5 times 10 to the negative 10. Thus, there are many fewer baryons than relativistic particles when the temperature is around an MeV. So basically, that's another way of saying that the Big Bang made a lot more of these, or right after the Big Bang, we had a lot more of the relativistic particles, such as the photons, electrons, positrons, mass, and the neutrinos that decouple from them, and way fewer baryons. This will also affect certain things that we will look at going forward. And of course, these baryons were pretty much mostly just hydrogen, because hydrogen, remember, is just the one proton. At this point, we're not really considering the elements as neutral atoms, neutral elements, or anything like that, because it's too hot and excited to be a neutral atom. So really, when we say elements, we just mean the nuclei. If the nucleus is that of a hydrogen nucleus, then we say it's hydrogen. So basically, again, in the Big Bang nucleosynthesis environment, way fewer baryons than there were the photons, positrons, and electrons, and we call it still the radiation-dominated universe. So one task, or our task in this section, will be to determine how the baryons end up. Were the system to remain in equilibrium throughout, the final state would be dictated solely by energetics, and all baryons would relax to the nuclear state with the lowest energy per baryon, which is iron. Stephen, hello. However, nuclear reactions which scale as the second or higher power of the density are too slow to keep the system in equilibrium as the temperature drops. So in principle, we need to solve the equivalent of a Boltzmann equation that we have mentioned, not really mentioned, but it's there for all the nuclei. That is a set of coupled differential equations. In practice, at least for a qualitative understanding of the result, we can make use of two simplifications that obviate the need to solve the full set of differential equations. The first simplification is that essentially no elements heavier than helium are produced at appreciable levels. So, oh, thank you. I'm enjoying studying because I heard that Donald Trump is banning TikTok and astronomy. I don't think astronomy can be banned. Steven says, hey all friends. Hi Steven. Thank you, Ella. Hi Doro. Hi Batman. So this is basically saying that this is Baji. Thank you. That's Baji. Thank you. Thank you for being here, Ella. Don't leave us. Be in the live. Welcome, welcome. So, one thing that actually simplifies matters for us for the Big Bang nucleosynthesis is the fact that we did not have very much elements other than hydrogen. Even helium we had pretty small amounts of. So it's not like we have to do a lot of math with a lot of different types of things when it came to the baryons. The photons, electrons, positrons we already covered. The neutrinos we already covered. And as you know, photons are bosons. We have Bose-Einstein for that. for the distributions if we need to. Positrons, electrons, and neutrinos, these are fermions. We have Fermi Dirac for that. So pretty much the only thing left at that point is the baryons. And, you know, for what it's worth, fortunately, unfortunately, there weren't many. So it's not like we have to consider a lot of complication in the Big Bang nucleosynthesis when it comes to baryons. So don't be afraid. We will cover it really quickly here today, okay? Big Bang, greatest event in the universe's history. We would not be here. I have to go to bed. Ella, good night. Baji's here. Yes, Baji's here. Thank you, everybody, for being here. Thank you, thank you. Thank you for joining. I know it's so quiet today. It's so quiet. I had to ban a couple of people. At first, I thought that they were going to give me an actual challenge. They said something I said about the neutrinos was wrong. And I'm like, okay, tell me. And then they were like, just the usual. Just the usual. When will someone challenge me on this channel? I'm so confused with the Big Bang. Yeah, there was a beginning. That's what we're talking about right now. How far back? What do you mean? The universe is around 14 billion years old, so that's how far back. So, okay. Sometimes it's good to be quiet. What do you mean? I kept going with the material, and it's shocking every time how stupid these people are. Who's Mike? Yes. Could it be that it was 13.7 billion years ago, but really it was 5 minutes ago? I don't think I follow. Maybe say that again. I mean, how far back in history, in galaxies and stuff like that, have they been able to find the exact age? So, do you know about the cosmic microwave background radiation? So it is true that it takes, so by the way, the speed of light is a constant in all frames of reference. So the light from faraway objects does take time to reach us, but the speed of light is actually one thing that is constant. Our space and time are relative, but the speed of light is actually a constant. But does it take a finite amount of time for light to reach us? Yes, correct. I'm gonna keep going. I'll let you elaborate on the question. So the first simplification of this soup in the Big Bang, or shortly after the Big Bang, is that essentially no elements heavier than helium are produced at appreciable levels. So the only nuclei that need to be traced are hydrogen and helium, yay, and their isotopes. So we will learn a little bit about that too. Deuterium, tritium, and 3He. The second simplification is that even in the context of this reduced set of elements, the physics splits up neatly in two parts. Since above T around zero point 0.1 MeV, no light nuclei form, only free protons and neutrons exist. Therefore, we first solve for the neutron-proton ratio and then use this abundance as an input for the synthesis of helium and isotopes such as deuterium. Okay? So now we will do a real quick introduction to nuclear physics. So the CMB is from when the universe was 300,000 years old. So very, very early universe, okay? So we will talk about it, don't worry. The cosmic microwave background radiation is very old photons. And remember we talked about primordial deuterium, how we can even get the baryonic density by using something like primordial deuterium. This primordial deuterium is literally from the very old days. We will talk about how hydrogen was made after the Big Bang, right? And that's what people mean. It's literally from very close to the beginning of the universe, okay? So lightning introduction to nuclear physics. And if you are interested further, then cosmic microwave background radiation, photons, and what we learn from those is going to be very helpful in understanding some of this stuff, I think, that we can look up and we can also... Oh, I see. I don't think she understands what I'm trying to say. I think it's a physics question. Put the speed of light as a constant makes sense. But what I'm trying to say is, how do you know for sure? How do I know for sure about the speed of light being a constant? Ooh, if you're interested in the work, which has to do with electromagnetism and how basically the speed of light being a constant kind of falls out of electromagnetism, and also this, it's almost like this insight, a deeper insight that Einstein had into that sort of work. And he brought it almost to another whole level in special theory of relativity. So we can talk about that too at some point. And we have in the past as well. Oh. Okay. So like you're saying, how do we know that 14 billion years? So 5 minutes where? That's what I would ask. I mean, Batman, everything is kind of based on observation too, right? So 5 minutes where? Because time is actually relative. So speed of light is a constant, but time, 14 billion is 5 minutes. Where is it 5 minutes? Are you joking or are you really with him? I can't tell. Hi, Robbie. Long time no see. Hope you're doing well. Thank you. You're joking. Oh, okay. I was scared, man. I was about to bring out the, do you understand English, Dora? So let me ask this. Speed of light is a constant. That's a fact of nature. Space-time are relative according to special theory of relativity. And general theory of relativity allows for accelerating frames, so you don't have to be in an inertial frame for relativity to work anymore. So space and time are relative, but if you're asking about this 5-minute thing, I would like to ask you 5 minute where? 5 minutes on Earth, 5 minutes on Mars, 5 minutes somewhere else. What do you mean? 5 minutes where? Because even the measurement of time is an observation, it's a measurement. You are empirically determining and saying some length of time is 5 minutes. So which 5 minutes are you talking about? Okay? I'll let you think about that. Like, are you saying, oh, 5 minutes on Earth? Well, 5 minutes ago on Earth, let's just take an inventory of what we have going on. We were still here. So human beings took a very long time to evolve. So that couldn't have happened in 5 minutes. The Earth is in its current shape. That also takes a very long time. The sun was a thing over 5 minutes ago. It went down, all that stuff. The sun is not 5 minutes old. Took a very long time to evolve to even get the sun. So it's like, it didn't take 5 minutes to get to this point, right? We know that. We are part of the universe. It's not like we're talking about some abstract topic. We're included in the universe. And we know that it took longer than 5 minutes to get here. If you look at the Andromeda galaxy and we see light from the galaxy that shined, yeah. So it's not the case that light is coming to us instantly. It does take time. It actually takes, our galaxy is 100,000 light years across. It takes 100,000 years for light to go from one end to the other end of our own galaxy, just our own galaxy. So we take into account the fact that light has a finite speed and it takes time to go places. Oh, Suji, you might want to clean your back. Your back end has a bit of a dingleberry. Goodness gracious, Suji. Oh, totally totally missed it. Oh, great. While we're struggling with your 5-minute question, you're not even here. 1 second, I gotta help out with Suji. Sachi! Hi, Sachi! Sachi, we need to do a little bit of a cleaning of your back. Sachi. There we go. Oh God. gosh. Okay. Had to do a little bit of cleaning. All right. Come. Come, Sachi, Mama. Here you go. Okay. All right. And we're back. Hello. Hello. Okay. So thank you so much, everybody. Sorry about the wait. Had to clean a piece of poop, actually. So we will keep on going. Lightning introduction to nuclear physics next, okay? Okay. So a single proton is a hydrogen nucleus. So I was mentioning how the Big Bang pretty much mostly responsible for just hydrogen and a little bit of helium. Pretty much for everything else, we can thank the stars, and by everything else, I mean the elements, heavier elements than helium, or even helium. Like our sun mainly makes helium from hydrogen. So we can thank the sun for all its heat and energy that comes from this nuclear process, right? So a little bit of nuclear physics here. So a single proton is a hydrogen nucleus, referred to as 1H or simply P because it's simply a proton. And as I was saying, how in the very hot and dense environment, you might not have neutral atoms yet. You might basically just be having the nuclei, and depending on which type of nucleus, that's the element that you have, okay? So if you just have one proton, Ben, we missed you. Sorry, there's a bit of a, I'm just making sure everything is good here. So if you just have one proton, we call that 1H, or a proton, or a P, or a hydrogen. If you have a proton and a neutron, that is deuterium. So we mentioned primordial deuterium last night. This is it. The proton and a neutron in the nucleus makes a deuterium, or 2H, or sometimes D. One proton and two neutrons make tritium, that's 3H or T. So this is still hydrogen and its isotopes. So when we say elementally, basically we just had hydrogen happening and coming out of the Big Bang. That's what we mean, hydrogen and its isotopes. Nuclei with two protons. So as soon as you get one more proton in the nucleus, now it's of course a different element. So two protons is of course a whole new element known as helium. These can have one neutron, so then it would be 3He, so two protons and a neutron. Or two neutrons, sorry. My brain had to buffer. So two protons and two neutrons, that would be 4He. Thus, unique elements have a fixed number of protons, and isotopes of a given element have differing numbers of neutrons. The total number of neutrons and protons in the nucleus, the atomic number, is a superscript before the name of the element. So by the way, atomic number is generally just the number of protons, as far as I know. I think this particular sentence might be a little wrong in this book. I think when we add protons plus neutrons, that's actually mass number. Atomic number is generally just the number of protons in the nucleus. I could be wrong. The total mass of a nucleus with Z protons and A minus Z neutrons differs slightly from the mass of the individual protons, excuse me, and neutrons alone. So keep this in mind. This is actually going to be very important because this is the concept of binding energy, which we've mentioned before, but we're just going to recap this. The total mass of a nucleus with Z protons and A minus Z neutrons. So if there's total A is the mass number. Hello. Hi, Reese. Hi, Stephen. Hi, Ben. Hi, Doro. Hi, everybody. Then you have A minus Z neutrons. So that difference, it's that mass, the total mass of the nucleus with Z protons and A minus Z neutrons is slightly different from the mass of the individual protons and neutrons alone. This difference is called the binding energy, defined as B, Z times MP, where MP is the mass of a proton, plus A minus Z Mn, where Mn is the mass of a neutron, minus M. This small m is the mass of the nucleus. And B is going to be some amount because the mass of the nucleus is not the same as the total mass of the individual masses of all those protons and neutrons. For example, the mass of deuterium, so listen up, this is going to be very important. The mass of deuterium is 1875.62 MeV, while the sum of the neutron and proton masses is 1877.84 MeV. So the binding energy of deuterium is 2.22 MeV. Isn't that so cool? The binding energy of deuterium is 2.22 MeV. So deuterium has that level of like a stability. It just, once it binds and becomes that nucleus, it's like, yep, I'm good. Yay. You know, just settles in to that particular more stable state of the bound state of that nucleus. Nuclear binding energies are typically in the MeV range, which explains why Big Bang nucleosynthesis occurs at temperatures a bit less than 1 MeV, even though nuclear masses are in the GeV range. Neutrons and protons can also interconvert via weak interactions. So I was mentioning how neutrinos interact via the weak interaction. So guess what? A proton plus a neutrino can actually make a neutron plus a positron, or a proton plus an electron can actually make a neutron plus a neutrino, or a neutron can break down into a proton, an electron, and an anti-neutrino. So these are some examples of weak interactions of protons, neutrons, and actually electrons, where all the reactions can proceed in either direction. The light elements are built up via electromagnetic interactions. For example, deuterium forms from P plus N going into D plus gamma. So a proton plus a neutron, because remember, deuterium is just a hydrogen isotope. Hydrogen generally just has a proton in its nucleus. So if you're saying you made deuterium, which is proton plus a neutron in the nucleus of that hydrogen isotope, you probably made this interaction between a proton and a neutron, giving you deuterium plus some photons, plus some energy out. Then deuterium plus deuterium can give you a neutron plus 3He. So basically, again, you're making a new isotope now. He is helium 3, meaning it has 2 protons and a neutron, isotope of helium. And basically, again, you can get this from 2 deuteriums. So you can see how if the Big Bang successfully makes hydrogen and hydrogen isotopes, you can actually get helium from that. It's not like the Big Bang has to make everything beyond, right? So really it's about that one proton, maybe one proton and a neutron type of thing. And back then, in those old early days when the universe was just getting started, we literally really only had very simple baryons. Literally, we're talking a few protons and neutrons here and there isn't enough of an abundance of these things to make the heavier elements. Because if you just kind of scramble together a few of these things, like, two deuteriums will give you a neutron and a helium-3. After which the helium-3 plus the deuterium can make a P plus a 4He, which is the helium-4 produces helium-4. So basically, again, how did we get helium-4, right? By stuff like this. The 3He plus the deuterium, again, making a proton. And that, again, maybe that proton wanted to get released, by something. So basically, in this type of energetic kind of environment, hot soup kind of environment, we didn't have much else going on. And also, because of the light, because of the rareness, the rarity of these baryons too, the king of the jungle, the more domination, the more dominant thing in the plasma was the photons, electrons and positrons. Remember, we talked about that. Relativistic photons, photons, electrons and positrons. Then the neutrinos that decoupled, those were part of the cosmic plasma. Baryons are almost like the universe's afterthought. Oh, let's make some baryons, which is just going to be mainly the protons and neutrons, and they can interact via the electromagnetic force or the weak force. And then later on, as an afterthought, we basically have some hydrogen and helium happening, especially helium happening a lot less at this point. So we that are made of baryons are really just an afterthought of this universe as it was getting started. We were not the main point of the early universe. The universe was radiation dominated at that time. Scale factor was a function of T to the 1/2, which is a different behavior than the scale factor when it became matter dominated. And very different life back then of the universe. Very, very different. Photons, electrons, positrons constantly interacting with each other in an equilibrium. Neutrinos, kind of part of that soup, but deciding to break up and leave. And then non-relativistic baryons, which are kind of few and far in between, eking out some hydrogen isotopes and some helium, but really a lot less helium than hydrogen. And if we had more helium, I asked this last night, if you had more helium, if you made a lot more of this 4He, 4He is basically 2 protons and 2 neutrons, right? So if you get enough of the 4He together, you might have made carbon, but there wasn't enough 4He at that time, okay? And we talked about binding energy as well. So binding energy, once again, class, what is the binding energy of deuterium? Somebody say it in the chat. Binding energy is a very important topic. It's a very important concept because we will see how the binding energy of helium is, of course, a bit of a local peak. And then the binding energy of iron is incredibly important and high. And this is why, yes, 2.22 MeV. Thank you. Yes. So because the binding energy of iron is so high, so you might wonder, why do all those stars? So we're talking about the Big Bang nucleosynthesis now, but later on we will make the first stars, and those first stars will die and make the next generation of stars, etc., etc. But why do we see all these like core collapse, supernovae type things to betray an iron core of stars? What is up with that? A lot of the times, the nuclear physics within these stars kind of stop at iron because iron is so stable. And that is why. And why is that? Why is that? Why is iron so stable? Because of binding energy. That's why binding energy is a very important concept indeed. Okay? and basically, the thing is that it's okay if you want to make something unstable, right? You just need different environments, right? If you're gonna do nuclear physics the super simple way, then of course you're going to get iron, because it's, if you want to pile on to the nucleus more and more and get a heavier and heavier nucleus, and it's going to naturally progress to something like iron, which is stable, and then it'll want to stop. But that does not mean that you can't go further. You might just need some more extra heat, temperature, pressure, other conditions, and then you can make heavier elements. So that's what I meant. Even within the stars, not the same process will make every element. Pretty much up to iron is going to be a type of process, and then the heavier elements beyond barium, actually, I believe barium is atomic number 56, are actually made in a different type of process. And eventually you'll see that there are a lot more neutrons actually in the nuclei than there are protons, and that whole process will be different. So that's more detail of nuclear physics that we won't probably get into today, but basically this is what is at the heart of it though. Nuclear physics, it's all about the nucleus. It's all about what the nucleus likes. It's all about the proton. I'm paranoid that I say the wrong word. Proton and photon are very different things. Oh God. Proton in the nucleus. So why is some iron in the Earth's core, but some is in the form of iron ore in the Earth's crust? So the reason why we have iron is not the same as why the stars have iron. As stars actually made iron, we just have iron. Why is some iron in the Earth's core? So we talked about how chemical differentiation happened and the heavy stuff sank. I'm not sure how much. There might be some iron in the Earth's crust because the differentiation is not perfect, but it might be from the, that's probably a valid reason, but I'm not an expert. Basically, we know that Earth had a bunch of differentiation, so the heavier stuff sank to the center and the lighter stuff is towards the top. But of course we have volcanoes, so some of the stuff comes out and up again. But the Earth iron story is very different from the stars iron core stuff that we were just talking about. But that's still a good question. Thank you. I'm so happy and proud that you're well educated. Thank you. Hi, Kimmy. Hello, Kimmy. Hello, Giancarlo. Is that right? Giancarlo? Ciao from Italy. Thank you. Ciao. Yay. Thank you, everybody. So this whole situation of the binding energy, basically, when you consider a nucleus, first of all, nuclear physics is going to happen in certain more extreme environments. Like basically making the hydrogen bomb, like nuclear physics is not like a chemical type of reaction, right? It's a more high energy, more extreme type of reaction. But this whole situation of adding the protons and adding the neutrons and finding some sweet spot of where the binding energy makes it the most stable nucleus, the tug of war between sort of how much energy you need to bring these things together to make heavier and heavier nuclei, and the release in binding energy, the release in the form of binding energy once it becomes a stable nucleus, that is what happens in the stars, in short. But also in the beginning, in terms of the Big Bang nucleosynthesis too, we had some of this, which is nice because we can talk about it. And thank goodness there were not really much of the heavier elements, so we just really have to talk about hydrogen and helium mainly when it comes to the Big Bang nucleosynthesis. I have a weird roaring noise. Oh gosh. So let's keep going. We will finish up this part. So both of these simplifications, no heavy elements at all, and only n over p, as in neutron over proton above zero point zero 0.01 MeV, rely on the physical fact that at high temperatures comparable to nuclear binding energies, anytime a nucleus is produced in a reaction, it is destroyed by a high energy photon. This is the other thing back then in the radiation dominated universe. Basically, even if you were trying to make something stable, you would get hit with a high energy photon and you're unstable again, you know? So it was really tough for the baryons back then. Yeah, it took a long time for us to get here because so much more maturing of the universe had to happen before we could come about, right? Because we're made of baryons. So, and baryons were not the dominant ingredient in the beginning. It took a very long time for all the stars to form and make more and more types of elements and do more things and then die and spew things everywhere and make big gas clouds. And then those gas clouds condensated and made something like our solar system. And then planetesimals were everywhere, or not everywhere, sort of. Condensations were happening slowly but surely. And then we were very molten. Then we cooled down because our mass was not as big, and we were also at a good distance from the sun. And then. So much stuff happened before we got here. Yay! So back to the Big Bang. So basically, at high temperatures comparable to nuclear binding energies, anytime a nucleus is produced in a reaction, it is destroyed by a high energy photon. This fact is reflected in the fundamental equilibrium equation to see how. Let's consider this equation applied to deuterium production. So there's some equation. I think this part is not, we can skip a little bit here and say that the small baryon to photon ratio, so a lot more photons than there were baryons. The fact that we're here at all seems bafflingly amazing. Well, it's just science. I was reading once about how we have no idea how life began and cannot recreate it in any way in the lab. We have no idea? Batman, you can always rewind and go listen to the parts that you missed. That's all right. More listening and learning and less fooling around is recommended for you by the doctor. The small baryon to photon ratio, meaning lot less baryons than photons, thus inhibits nuclei production until the temperature drops well beneath the nuclear binding energy. How cool. At temperatures above 0.1 MeV, then, virtually all baryons are in the form of neutrons and protons. Around this time, deuterium and helium are produced, but the reaction rates are by now too low to produce any heavier elements. We could have anticipated this by considering this binding energy figure I'll show you. The lack of a stable isotope with mass number 5 implies that heavier elements cannot be produced via the He4 or 4He plus P going to X, which is a new element. In stars, the triple alpha process, which I mentioned yesterday, 4He plus 4He plus 4He. So basically 3 4Hes or 3 helium nuclei with 4 mass number, as in 2 protons and 2 neutrons, will produce carbon! Yay! Because 2 plus 2 plus 2 is 6. We get 2 protons in each of these heliums, in each of the 4He. there are 2 protons and 2 neutrons. So 4He means the 4 is the mass number or the total number of particles in the nucleus. So 2 protons, 2 neutrons. So if you have 3 of these, you get, yay! You get 2 plus 2 plus 2, 6 protons and 6 neutrons, which is in fact C12 or carbon 12, which of course has 6 protons and 6 neutrons. So again, we need this triple alpha process with the 4Hes to make carbon in stars. But in the early universe, the densities were far too low to allow 3 nuclei to find one another on relevant timescales. So think about it. It was such a low baryon density kind of environment that these 4Hes could not find each other to make carbon. For that too, we needed stars. So incredibly different kind of environment. It's kind of like it was lonely for those helium 4s back then. They couldn't find other helium 4s enough to make carbon, and we did not make carbon. And here we are. We had to wait to be made because we had to wait for all the stars to form and more stars to form and die and all of that stuff before we could get even something as fundamental as carbon, really, from the periodic table. So literally every element above helium, and even helium, as you know, are made in stars. The Big Bang pretty much appreciably just gave us hydrogen and a little bit of helium, but really even that helium is probably coming from the deuterium stuff, doing other stuff, interactions to get helium, as we mentioned a bit ago. And that was it. Big Bang baryon story is really quite simple. So let me show you the binding energy per nucleon or type of particle in the nucleus picture here, where we will have MEV over A, as in the energy per mass number in the y-axis, and A, or the mass number, in the x-axis. So let me show you this picture and you will see how helium-4 has a local peak, making it very stable. And that's why helium-4 is a good nucleus to have. It has good binding energy type of story going for it. And later on, we will see how iron has the highest. So let me read this caption actually. And thank you everybody for joining. Thank you. Welcome to the live. Welcome, welcome, welcome to the live, everybody. Thank you so much. Thank you, thank you. Oh, thank you for liking the live. If we could get 20 likes, that would be amazing. And then Ben is saying that we are over 3,500. Yay, are we? Let me check. Are we over 3,500? Okay, that's what I was asking. Thank you, Kimmy. Kimmy says, I love hearing about physics here and there, so I subscribed. Thank you. Thank you for being here. Thank you for subscribing. Welcome to the live. Welcome. Thank you for being here. What's special today? We're talking about Big Bang nucleosynthesis. Thank you, Ben. Hi, Batman. Thank you, Nausat. Oh my gosh! Yes, we are above 3,500. Thank you, everybody, for subscribing. Let me think about that some more. I think I see what you're saying. Wait, is James here? Where? Oh, that's right. Morning from England. We're talking about Big Bang nucleosynthesis, my darling. I guess what I'm trying to say is theoretically. Doro, why do you not believe what James Woodlife says? He is perfectly capable of telling the truth here, I think. Hello from Belgium, James. That's right, we're all from Belgium. Some of the people in the beginning were asking where I'm from, and the mods weren't here yet. So I was like, let me wait for the mods to get here because they'll tell you I'm from Belgium. He's perfectly capable of making me laugh a lot. Because he's not. I believe him. James, I believe you. I believe James. From sorry, not England, Belgium. From Belgium. This live is kind of quiet, but at least it's better than the live from Monday where everybody was like fighting like cats and dogs in the chat. I was trying to teach something about planets probably. And like even looking at my phone was a distraction because everything was going zipping, and everything was a curse type thing that people were hurling at each other. I believe you wear your grandma's clothes as if it... Reese, be nice. For time to exist, space has to exist. Time is measured by what it takes to move from... Oh, the creator, okay. You know what? I was ready to laugh because I was a little bit feeling some pressure of like, I need to deep breathe in and out, I think. I missed a wild time Monday. Oh my God. On Monday, the fights here, nothing to do with physics, but people were fighting with each other constantly. I'm not joking about what I do. I believe you, James. Although the mods don't, apparently. Oh, can we get 20 likes, please? Reese? Don't say that. Te amo. Aww. You guys continue for a while. I need to deep breathe in and out. And then I'm going to show you the picture. One second. Here's the picture right here. Actually, let me show you right now. So do you see this? This is the picture. And in that local peak, it says 4HE, if you couldn't see, okay? So 4HE, as in helium-4, has a local maximum when it comes to binding energy. So it's a stable nucleus. Let me read the caption and finish this up because now we're into clothes. You know, James, whenever you come, these people don't believe you, and everything spirals. And he only comes for a little while too. James, what is with you? Why don't you say something physics related in the chat? What is all these talk about the clothes only? Could you please help out with some physics related comments as well? Wouldn't both perspectives be true? My mother is on holiday with her friend in Portugal, so I've got the... Who? Who are you talking to? Okay, I can't get distracted. This is too much. So this peak I showed you of helium-4, binding energy of nuclei as a function of mass number. Iron has the highest binding energy, like we were talking about, but among the light elements, 4He is a crucial local maximum. Nucleosynthesis in the early universe essentially stops at 4He because of the lack of tightly bound isotopes at A equal to 5 through 8. In the high-density environment of stars, 3 4He nuclei can fuse to form C12, like we said. But the low baryon number precludes this process in the early universe. So this process with the 4He was precluded in the early universe. We mentioned why. Literally, the baryon density was so low back then, we couldn't even get carbon out. But that's pretty much a very short, lightning fast introduction to just a little bit of nuclear physics for the benefit of you guys here. I think after this, I was going to move on to the moons of Jupiter and Saturn as my next topic. I wanted to take a little bit of a detour and talk about the universe, especially Big Bang and early universe type of stuff. I see there's a lot happening in the chat at the moment as well. I might take a breather and kind of look at your comments and whatnot. I'm glad that I got through that part before I am heavily distracted by whatever this is. What did he do? I'm just gonna relax around the house and watch some TV and wear her white silk What are you guys? I am reading. Do you see my expressions? James show. I read it with a filter. I'm just gonna relax around the house and watch some TV and just wear her white silk clothing and matching other clothing with the stockings. James, can you please say what is the most abundant element in the universe? And that will help my chat to get back on track. James is hilarious. Are you serious, Doro? You still find him funny? You don't even believe him. My mother is on holiday. Portugal is a warm place. I could see Portugal being a location of interest at this time. I've got the house to myself for a few days. Okay, that was normal. Oh my. Pigs are underrated. Face of stone as she's reading it. I mean, we've seen worse. Hide your feet. Pigs. What feet pigs are you talking about? I bet you would love to see me in it. Say hydrogenated. You spelled it wrong. Do you even know English? Reese, the Belgian. Hydrogenated. Hydrogen. James, what is the most abundant element of the universe? Chat, put it in the chat right now or I'm going to ban you. Enough is enough. You've been coming and learning nothing. High heels. Done working. You're still working. I'm not saying if people don't believe. I've had enough of this. And I have had enough of you not saying the answers to the questions in this life, which is that what is the most abundant element of the universe? Tell me right now. If James shows, what is going on? Hydrogen! Yes! See, Doro knows that it's hydrogen, the most abundant element in the universe. Okay, James will answer something. My cat likes your cat. Okay. I don't even know what you want me to say. James, say hydrogen. Listen to Reese. Why you're so funny. You look like Quicksilver from Fox Universe. What? Fox Universe? Like the production? Is that a production company? Hi, Ajay. Oh, that's right. This Ajay was here on Monday fighting about Nazis. My chat had nothing to do with the Nazis, but that's what he was fighting about with everybody. James, you're getting enough input from the others in the class. So if you don't learn and produce some kind of output, then that's really bad. I feel like the chat has found you to be, somewhat lighthearted. But at this point, I think we need to be productive. And we need to, okay, how about this, James? Can you tell us about the planets of this solar system? Tell us, name the rocky and metallic planets of this solar system. I'm leaving now. Excuse me, did I say you could leave? Quicksilver is the goat in Fox. Okay, thank you. don't know how that was not censored. YouTube is really confusing sometimes. I don't think he's that funny. He can't even name the planets. Energy? Hydrogen is the most abundant element, but now I asked him to, can you name the rocky metallic planet? Can you name the terrestrial planets? That's what we have been talking about for the last few days, James, and you've been here when I was talking about it, and all you do is this type of stuff. I know absolutely nothing what you just said. Not paying attention. All you do is this sort of thing. I'm not saying he's a troll. I'm just saying that he is extremely unproductive. Oh my gosh. Oh my gosh, oh gosh. Extremely unproductive. I'm not one bit interested in planets. Then why are you here, James? Why are you here? We just finished up cosmology. We're going to talk about planets. Why are you here if you don't want to talk about planets? Well. So we just did modern cosmology. Thanks to this break, because of James, I was able to breathe in and out a little bit. And now we will talk about the moons of Jupiter and Saturn. Lisa Ann? Oh. Reese, you pay so much attention to whatever he's saying. I like what Ajay said, to be honest. The thing you can learn from planets is that the world doesn't revolve around you, James. What the frick? Okay, Jupiter and and Saturn have many natural satellites. So now we're going to shift gears and talk about Jupiter and Saturn's satellites. I didn't ban him. Oh my God, now I'm choking. I asked about the rocky metallic planets. Batman. You're paying attention to every word of James. I didn't. Also, I like the name James. And this James is making it worse. Whatever. Jupiter and Saturn have many natural satellites. So now we're going to reference Foundations of Astrophysics. I'm getting a little cold now. At the time of writing, the number of known moons stood at 63 satellites of Jupiter and 60 satellites for Saturn. Although the count may well be higher by the time you read this. Yay! More moons. Most of these satellites are small and irregular in shape and are on highly eccentric and highly inclined, sometimes even retrograde orbits. The small irregular satellites are probably bodies that were captured after formation of the planet. Some of the satellites, however, are large spherical bodies comparable in size to the Earth's moon that have nearly circular orbits close to the equatorial plane of their parent planet. These large satellites were probably formed at the same time as their parent planet. It is found in general that small satellites are non-spherical, whereas the larger satellites are close to perfect spheres. Whether or not a satellite or other celestial object is spherical depends on whether its compressional strength is great enough to resist the force of gravity. The compressional strength of a material is the pressure required to significantly deform its shape. I looked over and now I'm completely distracted. I should not look at the chat. Hi, Marky Mark. The topic right now is the satellites of Jupiter and Saturn. It's okay. You guys can go nuts. We were talking about Jupiter and Saturn's moons. So, once again, the small irregular satellites are probably bodies that were captured after formation of the planet. Some of the satellites, however, are large spherical bodies comparable in size to the Earth's moon that have nearly circular orbits close to the equatorial plane of their parent planet. These large satellites were probably formed at the same time as their parent planet. We're talking about the moons of Jupiter and Saturn. It is found in general that small satellites are non-spherical, whereas the larger satellites are close to perfect spheres. Kind of like our moon is a pretty big moon and kind of spherical. Whether or not a satellite or other celestial object is spherical depends on whether its compressional strength is great enough to resist the force of gravity. The compressional strength of a material is the pressure required to significantly deform its shape. Engineers determine the compressional strength of different materials by putting a sample into a hydraulic press and increasing the pressure until the sample is either squashed flat or shattered, depending on how brittle the material is. So some of you guys are engineers, so maybe you will know about this compressional strength thing. Depending on how brittle the material is. So for instance, iron has a compressional strength of around S of around 4 times 10 to the 8 newtons per meter squared. So 10 to the 8, right? That's quite a bit for iron, that is. Typically igneous rocks have an S or compressional strength of around 2 times 10 to the 8 newtons per meter squared, similar to high strength concrete. So high strength concrete, compressional strength of around 2 times 10 to the 8 newtons per meter squared. Ooh. And solid ice has a compressional strength of 10 to the 7 newtons per meter squared. So these are all kind of like pressure numbers, sort of looking things, okay? For an approximately spherical body, we have found that the central pressure will be given by something like 2 pi over 3 rho bar squared, capital G r squared. The critical radius r sphere at which the pressure is just great enough to overcome the compressional strength and squeeze the object into a sphere is determined by the relation of P critical around equal to S, which is going to be given by 3s over 2 pi g to the 1/2 over 1 over rho bar. The values of our sphere for iron, rocky, and icy bodies are given in this table. We can look at. Let's actually look really quick. So minimum radius for spherical satellites. If the material is iron, the strength of which is 4 times 10 to the 8 newtons per meter squared, remember, then the R sphere for such a thing is going to be 210 in kilometers. If the material is rock, which the compressional strength is 2 times 10 to the 8 newtons per meter squared, the R sphere is going to be 340 kilometers. And if the material is ice, with around 10 to the 7 compressional strength of Newton per meter squared, then your R sphere is going to be 300. Okay, so the values of R sphere for iron, rocky, and icy bodies, we just covered that. The stronger of the materials of which natural satellites are made, iron, rock, and ice, are also the more dense. Thus, the value of our sphere is always around 300 kilometers and doesn't depend strongly on whether the satellite is mostly metallic, mostly rocky, or mostly icy. So look at this. Those sort of things, the ones we just listed off, were around 210 kilometers, 340 kilometers, 300 kilometers, right? So not like super duper different. So basically, they're saying the value of our sphere is always around 300 kilometer-ish, and doesn't depend strongly on whether the satellite is mostly metallic, mostly rocky, or mostly icy. But we still looked at this dependence on compressional strength. Of the spherical satellites in the solar system, 7 have radii of greater than 1,300 kilometers, or 0.2 of the radius of Earth, so pretty big, and thus are larger than any known dwarf planets. Somebody asked about Pluto. Pluto is a dwarf planet and is smaller than these moons, okay? These 7 giant satellites are listed. We will look at all the giant moons of our solar system. Our moon is one of the giant moons, actually. So pretty special, even though we just have the one moon, it is one of the bigger moons. So the giant satellites Ganymede and Titan are actually larger in radius than the planet Mercury. So the other day I was looking at, or asking somebody, I think, to tell me about this, but here it is, the information about the moon sizes. Pluto identifies as a planet. Its pronouns are small and round. Pluto is a dwarf planet. It's a dwarf planet. It's not a planet, but a dwarf planet. Okay, and it is smaller, quite a bit smaller actually. So 7 giant satellites, we will look at that. The giant satellites Ganymede and Titan are actually larger in radius than the planet Mercury. So even it's bigger even than Mercury. So of the spherical satellites in the solar system, 7 have radii more than 1,300 kilometers and thus are larger than any known dwarf planets. Reads what? Sometimes I'm reading the comments. But okay. So the giant satellites Ganymede and Titan are actually larger in radius than the planet Mercury, which, remember, Mercury had a radius of 0.38, the radius of Earth. The high mass density of the planet Mercury, however, means that its mass is greater than that of Ganymede and Titan combined. So remember, Mercury had a very high density, and we talked about the very rather large core of Mercury made of iron, of course. The 4 giant satellites of Jupiter are known as the Galilean satellites because, remember, Galileo discovered the Jupiter satellites for the first time after their discoverer, Galileo Galilei. As we discussed in the Galileo section, the Galilean satellites was an important early support for the Copernican system. In order of increasing distance from Jupiter, the Galilean satellites are Io, Europa, Ganymede, and Callisto. The Galilean satellites probably formed, as would, a miniature solar system. Ooh, the Galilean satellites probably formed, as would, a miniature solar system with Jupiter at the center. Do you even know English, Mr. Belgian? So Jupiter is kind of at the center of this miniature solar system of Jupiter. That is, the gas close to Jupiter was hottest, allowing condensation of only the least volatile substance, metal and rock, while the gas farther away was cooler, allowing condensation of the more volatile ices. Within the Galilean satellite system, we see the familiar pattern of decreasing density with increasing distance from the parent body. So Io has a row of 3,600 kilograms per meter cubed. We're talking densities, 3,600 kilograms per meter cubed. Europa has a density of 3,000 kilograms per meter cubed. And the 2 outermost Galilean satellites, Ganymede and Callisto, have a density of 1,900 kilograms per meter cubed. Around. Such a low density indicates that Ganymede and Callisto cannot consist entirely of rock and metal, but must contain substantial amounts of lower density ice. Io, the innermost Galilean satellite, is the most geologically active object in the solar system. Wow. When Io is viewed at infrared wavelengths, the hot spots associated with active volcanoes are readily visible. The colors of Io in the visible range of the spectrum are due to the presence of sulfur and sulfur compounds. So, did you know that Io is so active? Wow. Because of Io's low surface gravity, of course, because it's, not as massive. So the gravity on Io is only 0.18 g of Earth. Wow. The volcanic ejecta can rise high above the surface and spread over a large area. So imagine a volcano with less gravity. More Indian than Belgian. The volcanic ejecta can rise high above the surface and spread over a large area. Volcanism on Io results in a layer of ejecta more than 100 meters thick being laid down every million years. Wow, every million years, 100 meters thick of ejecta on Io. Thus, any impact craters that may be created on Io are rapidly paved over the volcanic ejecta. So we talked about impact craters, but of course, volcanic ejecta will pave on top of that. So the hottest volcanoes on Io are spewing out lava that is around 2000 Kelvin in temperature. This is too high an internal temperature to be maintained solely by radioactive heating. Io's dominant source of heating is tidal flexing of its interior. Because Io is so close to the massive planet Jupiter, it experiences large tidal distortions. The orbital period of Io is 1.77 days, is equal to half the orbital period of Europa, which is 3.55 days. The orbital resonance between Io and Europa causes the orbit of Io to change its shape continuously. Wow! Thus, the tidal bulges of Io are always changing in amplitude. The constant flexing of Io's interior as it changes shape causes interior heating. Io has a very tenuous, so around 10 to the minus 10 atmosphere of sulfur and sodium, which is continuously leaking away into the torus of charged particles around Jupiter and being replenished by fresh volcanic eruptions. So it has an atmosphere. It constantly gets leaked away into the torus, because remember the torus of charged particles around Jupiter, because Jupiter has a strong magnetic field, and it's constantly replenished, that atmosphere of Io, by its own volcanic eruptions, because apparently it is so very volcanically, or just active in general. The most geologically active site of the solar system is Io. We should go to Io. What are you sad about, Doro? Okay, actually, I'm cold. I need to get a jacket. Oh, actually, you know what? I will be charging my phone and going to the bathroom. And you guys can continue this vegan discussion. It is time. It is time, my lovelies. Can you like the live, please? Don't say that. They're gonna think it's really actually 3 hours. I'll be right back, guys. Promise. 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 Soon I'll be back. I don't. It's all done. I'm making sure. Oh, wait, it's not charging. Oh, no. Here. It's not plugged in. I'm like, why is it not changing? Okay. Everybody, stay. Stay and like the live. I'll be right back. And keep the discussions you guys are having. the discussions you're having, some of you guys are way too comfortable. My friends call me, you are vegan. Okay. Continue chat. What is DR saying? What was DR saying? Belgium is famous for chocolates. Is someone trying to give me chocolates? It's in Ireland. I'm sick and tired of being called a gooner. Oh God. What is this? Oh my God. Not yet, I don't. Not yet, I don't. On Twitch. Should I stream on Twitch? I don't know. I don't know. Ooh, can someone like the live? I won't. I need to stay on YouTube for sure. Definitely. Is it lame? Seriously? Wow. Okay, I need to make some tea. I'm around. I'm over here. I want to keep the phone charging and make some tea and then talk more about carbon. I don't know what you guys mean. Drink wine to truly enjoy what James said. Yeah, that's true. Where is my wine? Oh yeah, and where is that guy called Wine? He was coming to the lives a while ago. Oh, that's right. I have instant ginger chai latte. Look, I can drink this. Oh my god. It's so cold. I think I will make some tea. You guys keep on chatting. Magnesium. Oh good. I like it. You're talking about physics and science. Cesium. Hi Fuji. Fuji. Let me check the little robot. Sorry guys, we're back. Please like the live and we can talk about cesium if you like. Okay, where is my kettle? Boil some water. So, I'm glad everybody is still active. Oh, you're talking about the show? Oh yeah, I saw the first season, that was it. That's it for me. I know the guy who is the science advisor though for that show. Baji. No Baji. Baji. Do we have anybody from South Korea today? Mar Dala, really? Are you serious? You blame this stream? Mar Dala, Allah, Mar Dala, Allah. You can get Mardala on this stream. You don't need to go anywhere for that. Mardala. Mardala. हम पे ये किसने हरा रंग डाला. You can just request it, you know, Doro. You don't have to be shy. You can request a song. I can try to sing it. You can request a song. हम पे ये किसने हरा रंग डाला. हमें मार डाला. मार डाला. Tell me your top favorite songs. Haven't seen the movie in forever. You've seen the movie? It is a movie from my childhood. My favorite song is Dil Se Sathiya. So many. I don't even know. I have so many songs that I like. Sathiya. Mar dala. Allah. Sing Sathiya. My buddy loves Bollywood. Definitely can see many Belgian ladies enjoying it. Yes. हंसती रहे तू हंसती रहे हया की लाली खिलती रहे जुल्फों के नीचे गर्दन पे सुबह शाम मिलती रहे सौंधी सी हंसी तेरी खिलती रहे मिलती रहे साथिया साथिया Satya is kind of hard to sing, to be honest. There, I typed it. Satya, Satya, Madham Madham Teri, Kili Hasi. I'm glad the song appeared. Definitely took me back a few years. Sing Inhilogone. Wow! Look at the Belgian people giving me song requests. She's making Earl Grey from Jackson's of... I don't know what that is. I'm glad the song appeared. Definitely took me back a few years. She's making whiskey shots and drinking them in silence after what happened earlier in the chat. No, seriously. Absolutely. You guys should be sending me whiskey shots by mail after what happened. Oh my God. And it's always from Belgium too. Belgium too. These people. Reese, is it your friend? साथिया इन्हीं लोगों ने Probably not, I don't have friends. She's making whiskey shots. Indeed I am. Maybe. I'm gonna be making a chai latte. But yeah. Okay, what else? Dil se re, dil se re, dil se re. दिल तो आखिर दिल है ना, मीठी सी मुश्किल है ना, पिया 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 दिल से रे दिल से रे Obviously apart from Doro, I can be everyone's streaming pal. I'm a friendly internet cat thing. Aww. दिल तो आखिर दिल है ना, मीठी सी मुश्किल है ना, पिया 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 पिया. So I give you guys break time singing. What happened to that guy Ajay? He's the one who was giving me a song request. What's he doing now? Why is he not appreciating my singing? दिल तो आखिर दिल है ना, छोटी सी मुश्किल है ना, पिया पिया. The water is boiling. Yay. Maradala. He's making plutonium. Sky Harbor. Maradala. Hampe kisne hara rang dala. Maradala. Allah. Maradala. Hampe kisne hara rang dala. Shine. It smells good. Nice tea smells. Ginger. Ginger quick tea is what this smells like. I got 20 likes. Yay! Did James talk about tea? Because generally he only talks about one thing. And it's not anything other than that one thing. Stupid. Stupid Belgian. Doesn't even know English. Stupid. I actually like these songs. You had to become a volcano. Suddenly, you were like Io, an active volcano. Or no, an active, geologically active site. Most active on this, in this solar system. He's making plutonium. Sing Chandvi ka chand ho? What are these things you guys are saying? I don't know that one. I don't. James loves tea. Miss him. Well, he comes here to say those things and then you say that it's a joke, so that's why he leaves. If you want him longer, Mohammed Rafi. Wow, Reese. Reese knows his stuff. But then he leaves. I want him to stay and learn about planets and their moons. He does it seriously. I can't believe that. Why would anyone do that? I think it's dead serious. I think it's dead serious. I came into the stream to become. James entered. I had to become active. So some of these songs that are older, I don't know that well. You don't think it's serious? Baji! Oh, look at that. Here's Baji. Here's Baji. You don't think he's serious? Why not? Baji. Baji Baba. Here's Baji. Oh. Well, because I think he wants a platform to accept him. I think. Okay. So, this is Professor McGonagall. I love that. Marky Mark. I love this comment. Harry Potter jokes are welcome. I love it. Oh, I love Harry Potter. I love it. Oh my God. I didn't even think of that. This is full of McGonagalls right here. Yes, it's McGonagall. All right, I need some tea time. Ooh, what's another song I can sing in the meantime? What's my favorite Harry Potter movie? Well, I've read all the books, obviously. I've seen all the movies, obviously. You saw only one? What? My favorite book is the third one, Prisoner of Azkaban. Oh, serious. I've read all the books and seen all the movies. Na 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 na. And I've gotten the Harry Potter tour in Scotland, where she wrote the books in Edinburgh. La 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 la. And it inspired Diagon Alley and everything. Da 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 da. Yeah, I don't like when the people start dying so much. La 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 la. Yeah. Really? I think I missed that. Yeah, I will. I feel like I've seen that somewhere, but I didn't follow up on it because I've been an adult. I was probably more into it when I was kind of a kid, and back then, just read the books, saw the movies, that was it. I think he should have married Hermione. Oh, yeah. No. I just meant that I was not following her news too much. Absolutely. I should look it up. Na 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 na. Na na na. Oh, 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 oh. I cannot allow any inaccuracies when it comes to Harry Potter. No. No. You are fine, Doro. You're a good mod. But, yeah, it's fine. At this time. Marky Mark! Hello, Marky Mark. Hello, Batman. Who should really think through things. And Doro. And Reese. You see nothing, Batman. Name Jupiter's Galilean moons. Go. Shut up and name the Galilean moons of Jupiter right now. Google if you have to. You and your nonsense is throwing off the algorithm. Look at how many little people, look at how few people I have today. It's because of you. Jupiter's Galilean moons. Yes. Now. We were talking about it. Yes, Europa is one. And why are you helping him? I'm kind of looking too. But why are you helping him? Don't help him. Let Batman contribute something actually useful. Oh, sorry. Yeah, no, it's for Batman. He's doing nothing good in this chat. Batman, do you think this is Star Wars? Do you even know English? It's Io, Europa, Ganymede, and Callisto. I had to look it up too, but still. Ganymede is spelled as Ganymede. Stupid. Hi, Marky Mark. Hi, I'm Batman. Oh, you're the one that's bad. Hi, Jury Colado. Saludo. Hello. Actually, that's a good point. You should speak your nonsense in a different language so that I don't have to bother with it. Don't say it in English. Distraction. First language. We spoke about Io. It's a very active volcanic site. Io is the innermost Galilean satellite. It's the most geologically active object in the solar system. You heard nothing. You heard nothing, Mr. Batman. Well, for Batman, I don't know what to say. Is English your first language? And in fact, I would prefer it if you would say your things in a different language other than English. Thank you, Jury. Don't worry, everybody. It's only Batman who's getting batted right now. Not only does he not know the Galilean moons of Jupiter, he's also inaccurate on Harry Potter facts. Can you do anything well? Seriously, you belong in Azkaban. Europa, the next of the Galilean satellites, has a smooth, high albedo surface of A equal to 0.67. The reflection spectrum of Europa reveals 54% charge. Reveals that the icy surface is fractured into numerous ice rafts and ice flows measuring several kilometers across, similar to ice rafts seen on the Earth's Arctic Ocean. See? Doro likes Harry Potter. Harry Potter is the reason why he is not in a gang and is in Mississippi instead. What does that mean, Reese? I just looked over at my Mac and saw that. It's okay, we can just shoot the shit the rest of the night. I'm done. We will cover Europa at a different time when Batman is not here. I'm more of an anime guy, though. Oh, Doro, do you like Avatar? You know, like Avatar The Last Airbender? Harry Potter and the blockbusters are the reason why I didn't join the game. I had a good childhood. I saw the play in London. Cursed Child. Doro, did you see the full series? And did you see Korra? Batman, stop it. Last Airbender. He does not marry his... He does... What? I miss Uncle Ira. Korra ended on a really lazy note. Yeah. Loved Last Airbender. Yeah, I don't know. I don't do much anime watching, but I think Last Airbender is probably like my favorite show in terms of the anime stuff. I thought the live action was not good. I don't think I've seen Matilda yet. Should I see Matilda? You came back so you can learn. Fine, then contribute something to the chat other than nonsense. Can you say what is the mass of Mercury in terms of the mass of Earth? We covered it in this live, a couple lives ago. Free Reign Beyond Journeys. It's the anime I tell all girls to watch. Oh, thank you. Solid show. Very emotional. Aww, Roald Dahl. Especially Boy, which was kind of an autobiography. I feel like, yeah. Okay. I'm Batman. You can chill out. It would be nice if you could say some scientific fact soon here in the chat, though. I'm making a serious request. You look like Katara. Katara was the sister, right? The waterbender? Am I remembering this correctly? We don't want to know about daily anything from him. Oh my god. I can only imagine. In fact, I cannot imagine. Aang is the brother? Why? Why were the comments removed? Was it like automatic? I think I liked Korra because it had a lot of action. Oh, thank you. Thank you. I forget myself what I've said. So Korra had a lot more darkness, right? And it had a lot of action. It's been several years since I watched all this, though. She went off with that other girl, right? Did they get married? I think so. Korra's good. Legend of Korra. So after the first Airbender series, Avatar: The Last Airbender, the next season is Korra. Legend of Korra. Yeah, exactly. That's what I think too. Legend of Korra, watch it. But I think The Last Airbender is more like the original good one. Yeah, Korra is a bit more dark. But I think it was nice, like how she was struggling with getting all four, you know? It's not bad if you expect it to be sort of like its own thing. like don't expect it to be like Avatar, but if you're okay with it being its own show, basically, then it's not bad. Hi, Jerry. Mm-hmm. Mm-hmm. Like I said, Reese, it's like the only animation stuff I like. I'm not big into anime. I'm not big into like animated shows and stuff, but um but I liked Airbender. I like Avatar and Korra. Or I liked it. I basically watched it years ago. Yeah. I don't think it's a kid show. It's a, it's a show. I don't really I'm not really watching a lot of shows these days, to be honest. I don't really watch a lot of TV anymore. Can't watch shows much. Yeah. I'm not really into any show right now, to be honest. Just like working and stuff. Hi, dear. Hello. TV is kind of just work programming for the nation these days. Wasn't it always like that? But yeah, I'm not really watching much. Actually, there is a show that I kind of liked on Netflix. It was called Virgin River. I kind of like the show. It's like sort of peaceful. I think I'm gonna cover Europa with the kids tomorrow in the afternoon timeline. Batman, you can feel free to not come since you are useless. $20. You can come at night. You can come at night. I'm embarrassed by you at other times. You can come. You can come during the night chat. Mhm. Exactly. We're shooting the shit now. So now it's fine. What other girl? Yeah. Shooting the shit now, so anything is good. But when I'm covering Europa tomorrow, for real, and I'll have to recap IO because of certain people and their mother's clothings, and you. Are you serious? They never liked me. So this is not a new phenomena. No shit. He's gone. What happened to my Australian? There was this Australian guy. Peter, are you here? Good day, Peter. If you're seeing this later. Peter later. You're only like 13. People come and go, they will return. Surprise my boy. Wait, Batman, are you only 13? Are you only 13? Because that's really bad. This chat was not very family friendly. I hope you're not a child. Marky Mark, I had not seen you in a really long time, so appreciate you coming to the live today, by the way. I feel like I've seen you a long time ago, and then there was a big gap, and then you came today, so thank you for being here. Welcome to the chat. Sorry it's so crazy, Marky Mark, but good to see you. Hopefully you caught the Big Bang stuff in the beginning. Wictopo! Lol, this chat, yeah. Sometimes I wonder what it is that is going on. So so I heard you where did you Where did you hear this, Reese? Where? Ew. Actually, I've never been to Chuck E. Cheese, to be honest. Because I didn't grow up here. Nobody took me to Chuck E. Cheese. What the heck? Nobody has taken me to Chuck E. Cheese. 3 rich boyfriends. You clearly did. Wow. Wow, Reese. Wow. She's not telling us. That's because, Reese, I just went swimming. And I did that today too. I went swimming. I went swimming and I felt just really happy. And I did that, went swimming today as well. Then I came here. That's it. At the gym. Well, I don't care about anyone. I hope everyone is happy and fulfilled in whatever manner they want. Batman, keep your mouth shut. Stop it. Stupid. In fact, I will ban you now for 30 seconds. Where are you? Enough is enough. 1 minute. 1 minute ban on... Did I do the right person? Oh, yeah. Anim cat. Hi, Sachi. Come, Sachi, come. Sachi. Oh, look, Sachi's waiting for me. It was just swimming. But I was happy. Happy and fulfilled indeed. Professor McGonagall. Yes, let me show you the next Professor McGonagall. Sachi. No. Can we hug? She's dating a lifeguard. I know. Fur is flying. This one, she's very picky about hugs. She's over here though. She was right here. She was waiting for me. And then I looked at her and she was like, yes, I'm here, I'm here. She was like this. And so I picked her up. She was like, hi, mommy, mommy, like this. Sachi, mama. Sachi. Reese, where did you go? Why don't you say something about yourself? Did you go to Chuck E. Cheese? Hello everyone, welcome to the live. Currently we're just talking about nothing. Generally speaking, we talk about physics, astronomy, astrophysics, and cosmology. I did do that earlier today. If you rewind, we talked about Big Bang, nucleosynthesis. Right now the guys and girls, I don't know if there's any girls, are talking about not too much. You're welcome to join, and especially welcome to rewind and watch the whole thing. I went on a date last week. Was fun. 2 anime cats watching the movie Nosferatu. Nice date last week. 2 anime cats watching the movie Nosferatu. Oh yeah, Batman is back. Was that 1 minute? Went really fast without you. I haven't been out of the house in like 3 weeks. We talked about Big Bang nucleosynthesis, and then we started talking about the moons of Jupiter and Saturn. See you in 2 seconds. What do you mean? So, rewind, guys, if you're joining. No, don't say that. Oh my God. Oh my God. Okay, I'm gonna close this. Shokuni Mama. I am good. How are you? আমি ভালো আছি। আপনি কেমন আছেন বলুন লাইভে। Here's my friend joining from India. I mean, I don't really know him, but here they are. Can you please like the live? Like the live. Right now, please. Thank you. He's from Belgium. That's very true. बहुत दिनों बाद आई. I go live almost every day. You're the one who has not showed up. Or maybe that's what you're saying. I need to go see my parents. I feel pretty awkward around my parents. Sometimes like 6 months has gone by. Didn't you do Christmas with them? हाँ जी, खाना पीना हो गया. Reese, you did Christmas, right? With them? Don't mention that guy anymore. Saw my mom, but I haven't seen her. Okay. Well, that's something. That is something. Yeah, makes sense. Good night, Doro. Have a good night. I don't think you're messed up. They're around. Time for their bedtime, too. Thank you for sharing, Reese. It's a tough topic. Good night, Shokuni. So I've been going live right around like 11 p.m. EST pretty regularly. Sometimes I go live in the middle of the day, like afternoon-ish time EST as well. You should subscribe and turn on the notification so that you get notified when I do go live. Marky mark. And pretty much it's most days. So I hope to see you soon. My family are pretty mental. I feel like that's a lot of families, but yeah. I think you can overcome them. You know, see them maybe sparingly, but don't let it affect you. Keep you from being happy. 4 is very young. The UK has a lot of trains. You could take a trip up to Scotland or up to Scotland. What about a train trip? Solo travel? Solo trip to Edinburgh? Ooh, and then you could tour all the castles there by yourself. Don't have to hang out with other people for that. I did that by myself. Solo trip. Ooh, solo trip down to Paris. Take another train. Take a train down to Paris. Stressful how? Like you have to schedule things like that, you mean? Or that's okay. You could have maybe like a phone with like a charging pack so that you know that like your phone will always be able to get charged and you can use Google Maps or something. So that basically you can always navigate back to the place. Sometimes, so I depend heavily on my phone for all kinds of things like navigation, right? But one panicky thing for me is that what if my phone dies because I'm using it too much? So my friends made me get this charging thing. I think they just want your help with moderating. That's what that means. It's fine to have autism. You could still kind of, you know, do your thing, help figure out like what could mitigate some of the fears. And then you could go out and see the world, you know? Take trains. The trains are really good there. Oh, yeah. Yes. Take a long walk. Walks are the best. Walks are the best. Take a long walk. That sounds good. Actually, a daily walk is really nice. Daily walk. Get out. I try to do a daily walk or the swim thing that I was mentioning. I either try to do a walk in the afternoon, like when it's still kind of sunny out, or I try to go and swim in the evening. Yeah, I can keep chatting, but I'll wrap up the live. Good night, everybody. Thank you for being here. Of course. I really recommend some sort of daily thing like that. Daily walk or some kind of activity. Sounds as if you're beset by social anxiety disorder or equivalent. Many medicines can help with that. Oh wow. Yeah. I mean, to be honest, if somebody like rang my bell, I'd be pretty anxious. I kind of have the same thing. But maybe you have that but like more extreme. So just kind of some practice with going outside and walking might help. And then you come back. You can still be a hermit. Just get your daily walk done and then be a hermit again. You can make the changes like slowly, step by step. I put your picture in my blindfold. Blindfold? I don't know what that means. Oh, I see. I think I get it. The thing that blocks light. I see. Clonazepam. Clonazepam is one med that deals with that. Thank you, Ben. Yay, Ben is helping. And here is Sachi Mama, also helping with her tail. Hello. Hi. I'm sorry, Sachi, that I picked you up. I'm so very sorry. Hi, baby. Hi, Shona. Come. Hola, Baba. Oh, you're such a cutie. You're such a cutie. She's perfect. Yeah, Sachi. Sachi is. Hello. Hi. Hi, do you want to rest your face in my hand? Do you want to rest? She wants to rest her. She wants to rest her face in my hand. Ben, are you a doctor? Yes. There we go. That's right. That's a great comment. Reese, speak with a mental health expert. They can help resolve your trouble. Yes. No, but I have family who are afflicted by Reese's problem. I'm the reason people exist. I have in the past, but they just put you on what I call zombie tablets. Well, could you speak to them about like avoiding that? Could you be like, hey, this particular medication like really didn't help, so laugh and learn. Yes, that's a good thing. Could we not do that one? There's Baji. There's good doctors there, right? They can hopefully address that. There you go. Look at Ben. Ben, you're on fire. The right dosage should prevent that zombie state. Reese, I think you're doing that thing where, you know how when I was talking about the impact craters and you just didn't want to listen? Be open to it. Be open to the mental health experts. And don't assume that they are against you. Not all of them. Maybe you can try a different one. There's got to be somebody who can help with a more wholesome approach. Yeah, no, I feel you. I understand the bad experiences you might have had, but we must still strive for a solution. Okay. Oh my God. I read this comment and I thought that was Ben. And I'm like, what happened to Ben? Thank God, it's just you, Batman. Shut up for a second. Jesus. I saw this comment. I was like, Ben is saying helpful things. Yes. Oh, good job. Thank you, Ben. Non-metric is to walk out your door by pretending you're an actor, not yourself. An actor who is confident and more outspoken. Imagine you're in a film. Yes. Yes. Can you do that for the walking part and just, for now, just focus on the walks? You could have like, I don't know how safe it is, but you could have like headphones in so that people don't try to talk to you, so that you're still not doing the social part, but you're getting outside and walking. But I don't want to recommend anything. I think walking outside with the headphones in is a little bit dangerous because you might not hear something coming. You know what I mean? So just be safe. We're just friends. We're not health experts, obviously. Good. Yes, that sounds good. Start going for walks. Yay! Go on a walk and tell us next time. No, it's a relevant topic. But next time, tell us about your walk. Maybe like an afternoon walk or something. And just be careful. Don't get hit by anything. Watch out. Check both sides when you're crossing the street. Thank you, Ben. Good job. I'm gonna turn these lights off. Sachi. Thank you, everybody. Oh, Sachi's here again. Sachi. Okay. She doesn't want to be picked up. Sachi. Okay, we use this book today. This is the old book. as well. Good night, everybody. Good night. Sleep tight. Walk, walk. Hi, Swatchy. Hi, Swatchy. Okay, okay, okay. Aw. Scooby-Dooby-Doo, where are you? Scooby-Doo was always scared of ghosts. That's right. Scooby-Dooby-Doo, where are you? Come on, Scooby-Doo. Come on, Scooby-Doo. I think too. Da-dum-dum-dum-da-dum. Scooby-Dooby-Doo. Scooby-Dooby-Doo, where are you? Baji's up. And Suji. Baji. Baji, Baji, Baji. Hello, Baji. Hi. Baby to me. Actor baby. Scooby-Doo, where are you? Scooby-Dooby-Dooby. Aww. Such a cutie. Such a cutie. Such a cutie. Charge the Mac. You can hang out if you want, Sachi. Look at this. You're so cute. You're so very cute. Here you go. Here you go. Here you go. Oh, all right, everybody. Look at that. Oh, so cute. You can hang out still. You can hang out for a while if you'd like. Monica. Oh, my darling. Oh, good job, Baji. Good job. Keep going. You're such a cutie. You're such a cutie. You're such a cutie. Here's Baji. Charging. Say bye. Say good night. Good night.